So I was talking about the column volume before the recording was cut up. So the one column volume equals the same volume as the column size. So when you say two column volume, that means whatever the volume of the column is. If it's a 1 liter, that's 2 liter. Okay. If it's 10 to 20 column volume, that's about 10 to 20 liter of buffer that is used to maybe wash the column. So that's a proper sample loading using 2 column volume, about 2 liter of buffer. That's the washing that's done with about 10 to 20 liter of the buffer. And then finally elution is done with about 1 or 4 column volume of the buffer. Okay, and then again 2 column volume of the buffer. Okay, so x-axis showed you how much of the buffer was used to run your chromatography system, okay, from the beginning to the end. Okay, so it's 2 plus maybe 20, that's 22, plus 4 is 26, plus 2 is like 28 column volume. Okay, and then if you look at the UV light, it shows you different protein peaks are coming out at different time point. So maybe first peak of the UV absorption change, that means there is a fraction of protein came out, probably protein with the same property. Okay, as soon as the sample was loaded, it came out. So probably it has almost no interaction with the column, it just comes out. And then second set of protein came out, third, fourth, it continues, okay, until the last peak came out at the proper elution stage. Okay, so that's what this UV absorption change shows you. And then the red line, I told you that's the conductivity change, right? During the sample loading, you are using a very low salt because the conductivity was at the basal level. And then during your washing, you see your conductivity is slowly coming up high. So that means you're increasing your salt composition during your washing, okay, step. And then at the elution step, the salt composition suddenly jumps, so you have a high conductivity. So that's probably elution buffer that has high salt in it. So that salt buffer is used to compromise the interaction between your resin and this target protein. Okay, and once that's done, you'll bring down the salt composition again by introducing probably the buffer without salt. Okay, so that shows you the change of the buffer composition, almost low salt, and then washing, slowly increasing the salt, and the very high salt is where the elution is taking place, and then regeneration, meaning you are washing off the salt from your column. Okay, that's the process of the chromatography. Typically that is the ion exchange chromatography run that is done this way: low salt sample loading and increasing the salt composition, that's the washing, and the elution is done at the high salt, and the regeneration of the column again at the low salt composition. Okay, and then so the chromatography system, like I told you, that's the one in our lab, and that's another one in our lab as well. So that's a biological LP system. It's a very good system where you can learn your chromatography run. And this is a GE ACTA chromatography system. So it's a very good system, almost GMP scale. So Catalan's PD group has this. Okay, and this is a large scale chromatography system. So these are kind of bench scale. That's a large scale. Okay, and this shows you the process of a downstream process. It came from actually Catalan. So when they try to purify their antibody target molecule, so a lot of their API molecules are made up with antibody, monoclonal antibody. Okay, they typically use this kind of process. Okay, so this is a downstream process for one of their manufacturing projects they are doing for their clients. Okay, so the first step is protein A. Protein A is what? It's an affinity chromatography run. Okay, so one chromatography run here, and then there's a low pH. So normally affinity chromatography run is done at a low pH composition when you do the elution step. So that's low pH ending of the protein A column, and which can be used as viral inactivation because at a low pH viruses are inactivated. Okay, and then there's a second chromatography run. Okay, so that is CEX. CEX means what? Cation exchange chromatography. There's a second chromatography method done, and then there's a polishing, another chromatography method following after that. So that could be either anion exchange chromatography or mixed mode chromatography or HIC. HIC means hydrophobic interaction chromatography. One of those three can be done. Okay, and then so after that, viral filtration, maybe nanofilter or ultrafiltration will be done, and then UFDF, ultrafiltration, diafiltration, to do the formulation. So in this downstream process, how many chromatography methods are used? 1, 2, 3. At least 3 different columns are used, right? And then how many filtrations are done? So you can see at least 1, 2, so at least 2 filtrations done. Okay, so that makes up the entire downstream process. So what it shows is what they use multiple chromatography runs to purify their API, as well as multiple, filtration, diafiltration, ultrafiltration, or viral filtration. So filtration and chromatography run are very important. Those are bread and butter for the downstream process. Okay. So what kind of resin or column medium can you use? It depends on what column resin do you use. Chromatography methods can be called in several different kinds. Okay, so number 1, chromatography column resin is called gel filtration. Okay, or permeation chromatography. So gel filtration or gel permeation chromatography, it's GFC or GPC. Okay, so it's just like a filtration method. Okay, another name for that is SEC. SEC is what? It's a size exclusion chromatography. Size exclusion chromatography. It's basically what? Size-based separation method. That's what it is. Okay, so the difference is the smaller molecules come out later than the larger molecule. So how does that work? So your resin is made up with these resin beads. Okay, but the special thing about these resin beads are they have small holes in them. Okay, so if you have a mixture of large and small molecules, okay, the small molecules can go through these small holes that exist in the resin molecules, while the larger molecules cannot go through those small holes. Instead, they just go around the large molecules. So if you compare the speed of these molecules running through the column, of course, smaller molecule will have longer distance because they'll have to go through all these holes continuously, so they'll come out much later than the large molecules. They'll just run through the large molecules and they'll come out fast. So yeah, gel filtration, so they're filtrated by small molecules, so small molecules are coming out much later than the large molecules. So you can use this chromatography method to capture and maybe purify out your API molecules, a size-based separation method. Okay, so that's the first one, gel filtration or gel permeation chromatography method, or another name for that is size exclusion chromatography method. Very simple kind. Okay, used for purifying your API against like high salt or maybe small peptides and things like that. Okay, and the second chromatographic column is normally made out with some ions on the resin. So we call that ion exchange chromatography. Okay, ion exchange. So your resin can have anion or cation. Okay, so your resin is made up with either anion, cation. So which means then the opposite ion will be binding with your resin and will be retained by your column. Right, so that there's going to be ionic interaction happening during your chromatography method. So think about it. Let's say your column has maybe negative ions, so it's they are what, anions there, and if you add the mixture of proteins that are added, so then if the resin is negative ion, then which one will bind? Positive ions will be bind, right? So the negative ions will come on first, and then positive ions will come out later. So that's how this interaction works. So anion exchanger, cation exchanger depends on which charge molecules, resin molecules you have on the column. Okay, so anion exchange chromatography means anion will stick to the resin that is cation. Okay, cation exchange chromatography, that means cations will stick to the resin that is an anion. So that's how the nomenclature, the naming is done. Okay, so in this case, the resin has what? It's probably a positive ion. okay? And then probably then which kind will bind? So negative ions will be binding, right? And if this and so yeah, so the elution will be done by challenging the interaction with the high salt, and then high salt will bump up the bound molecules, okay? So the resin will have all these charged ions in them, okay, to attract, opposite charged molecules. So exchange means the binding will be exchanged during your chromatography method. Okay, think about it. So your column has probably positive ions, then it will bind negative ions, right? So the sample injection, when it happens, whatever that was still binding on the pocket will be exchanged first when these new anions come in and bind, right? And then during the washing, weakly bound ones will be washed away, and then finally the elution will be taking place when you challenge these ones with the stronger anions. Okay, that's the elution. So there'll be exchanging of the bindings happening during your chromatography run. That's why they are called ion exchange chromatography. Okay, hope that makes sense. So again, these are the resin, okay, molecules that are charged, maybe negatively in this case. Okay, now they will be attracting the positively charged target molecules. Okay, negatively charged proteins will not bind, they just come up right away. Okay, and then that binding will be challenged by high salt, which will have a higher concentration of charged ion, in this case maybe potassium, which is K pluses. If we had maybe 2 molar potassium chloride, they will come in and exchange the bound proteins with them. Okay, so that's what exchange means. Okay, so these are commonly known anion exchange or cation exchange columns. Okay, so weak anion exchange columns. Okay, so DA cephacel or DA cephadex or PEI cellulose. Okay, they have these functional groups that are positively charged. Okay, and then they have medium made out of those polymers. Okay, and cation exchangers, so the resins are anions, of course. They have names of CM cephacel or CM cephadex or BIOT212 Okay, so they have this functional group, carboxymethyls. Okay, different kind. So these are their chemical structures, negatively charged, right? So negatively charged. So they'll bind with the positive charged ion, which are the cations. So cation exchanger is the name for these guys. And then these guys will have positive charges, right? So they have positive charge, so they will bind with the negatively charged anions. So they are called anion exchangers. Make sense? So now I'll stop it right